Chapter 1, Section 11, Digging Deeper, Recording Earthquake Waves, Seismometers. In the Investigate, you built an instrument to detect and monitor ground motion. You also examined data that were generated by a seismometer. A seismometer, also known as a seismograph, works on the principle of inertia. Inertia is the tendency for a mass at rest to remain at rest. Seismometers, similar to the device you built, were first used in the 1800s. They had a cylinder coated with soot. A stylus scratched a mark as it registered vibrations. In today's instruments, the relative motion between mass and its frame creates an electrical signal. The signal is then increased. It is then passed on to a recording destination. Sometimes ink pens make the recording on paper. A narrow beam of light can record the vibrations on photographic paper. The recording might be made by a device that records a magnetic signal on tape. It can also be on a computer screen. It takes 3 seismometers to record all the motions of the ground during an earthquake. 2 horizontal cylinders at right angles to each other record sideways motions, north, south, east, west, and the third cylinder is vertical and records up and down motions. Let me scroll down a little bit so we can see what it looks like. The seismometer. Instruments used to detect earthquakes are attached to the ground. They record any motion of the ground to which they are attached. These motions can be natural. For example, the ground can move as a result of earthquakes or landslides. People can also cause the ground to move. Large trucks, passing airplanes and helicopters, and blasting during construction can also cause movement of the ground. Figure 1. In the 1960s, a worldwide network of seismometers was developed to verify nuclear test ban treaties. When a nuclear device is tested, seismometers around the world record the seismic waves that result from the blast. Interpreting seismograms. A seismogram is a written or mechanically produced record of earthquake waves. You just read about different ways these records are produced. Figure 2 shows a seismogram recorded in Dallas, Texas. Note the separation of P waves and S waves on the seismogram. This seismogram was recorded about 1,600 kilometers from the earthquake's epicenter. If it had been recorded closer to the epicenter, the 2 waves would appear much closer together. All the waves are produced during the rupture. As distance from the epicenter increases, the separation and arrival times between the wave types increase. That is because different kinds of waves travel at different speeds. P waves travel the fastest through Earth. Therefore, they arrive first at a distant station. S waves arrive shortly after. Waves that arrive after the direct P waves complicate the seismogram. Various reflected and refracted P and S waves bounce off and along layers of the Earth's interior and eventually reach the station. This is a seismogram recorded in Dallas, Texas. This is a travel time curve for an earthquake. Here we go. Using travel time curves. P and S waves travel at different speeds, so they arrive at different times at a seismological. Hold on, 1 second. Okay. P waves travel the fastest through Earth. Therefore, they arrive first at a distant station. S waves arrive shortly after. Waves that arrive after the direct P waves complicate the seismogram. Various reflected and refracted P and S waves bounce off and along layers of Earth's interior and eventually reach the station. Using travel time curves. P and S waves travel at different speeds, so they arrive at different times at a seismological station. The difference in their arrival times increases with the distance from the epicenter. Travel time curves show this relationship. See Figure 3. The graph shows the data from a magnitude 8 earthquake in the Kuril Islands on December 3, 1995. Here you can see the relationship between the distance and the difference in arrival times for P waves and S waves. Seismology and the study of Earth's interior. People have always been fascinated by Earth's interior. To this day, the deepest hole ever drilled into Earth's crust is in the Kola Peninsula, Russia. It extends more than 12 kilometers into continental crust. However, that crust is 70 kilometers thick in places. Volcanism rarely brings up samples from deeper than 150 kilometers. This means that no one has ever made direct observations of Earth's deep interior. In section 2, you saw a diagram showing the concentric structure of Earth's crust, mantle, and core. Earth's radius is 6,378 kilometers. This is a well-established fact among scientists, but how do scientists know the depths at which Earth's interior properties change? The answers come from the application of physics to geology. Since the 1900s, scientists have used seismic waves to study the interior of Earth. Physicists have found that seismic waves travel much faster through rigid material than plastic or soft material. This means that changes in the speeds of seismic waves can be used to make inferences about what makes up Earth's interior. In science, there is a difference between velocity and speed. In this section, assume they mean the same. You may have seen this change in speed of waves when you looked at a straw in a glass of water. When you observed from the side of the glass, the straw appeared to be broken at the boundary between the water and air. Note that the thin glass causes very little distortion. This occurs because light travels at different speeds in different media. The light rays bend when they pass from one medium and into a second medium. This process is known as refraction. Because the light is traveling in different directions from the glass into your eye, a visual distortion occurs. Your brain determines the location of the straw to be at the place where the light rays originate. Because the eye and brain assumes light travels in a straight path, the brain misplaces the location of the straw. As a result, the straw appears to be broken. The refraction of light rays moving between water and air makes this straw appear distorted. Imagine the inside of Earth to be completely uniform. What would happen to seismic waves traveling from the surface into the interior of Earth? The waves would travel at a constant speed. This is shown in Figure 5 using wave rays. Wave rays are the travel paths of lines drawn perpendicular to wave fronts. In a uniform Earth, wave rays travel in straight paths without bending. So Figure 5 shows Earth's interior were completely uniform. Wave rays would travel along straight paths. Figure 6 is showing that if Earth's interior gradually increased in rigidity with depth, wave rays would travel along curved paths. Now imagine that Earth's interior gets more rigid with depth. In this case, the speeds of seismic waves passing downward through Earth would increase with depth. This is shown in Figure 6. Let me scroll back up. This is shown in Figure 6. The speed of the waves would increase, causing the wave rays to bend. That is because the wave rays move into a more rigid material deeper in the interior. Wave rays would follow a curved path. If the speed of the waves and the distance they travel is known, then scientists can use any acceleration, change in velocity, as an indication of a change in the media through which they travel. Okay, so it's saying if the scientists know the speed of the waves and the distance they travel, then they can make that calculation. All right. Data from studies of seismic waves has shown that waves change speeds as they pass through Earth's interior. They speed up or slow down depending on which part of Earth's interior they travel through. This would not happen if Earth's interior were uniform. From this, scientists have concluded that Earth's interior is not uniform Instead, the speeds of seismic waves suggest that the physical properties of Earth's interior vary with depth. Seismic waves are believed to bend as they travel through the Earth. Figure 7. Okay, here's figure 7. All right. Figure 7 shows how the wave rays from an earthquake's P waves radiate through Earth's mantle and core to reach distant locations. The behaviors of the rays depend on their directions and media they encounter. Notice how ray 1 bends gently within the mantle and emerges at the crust. All rays bend gently within the mantle. This is because the mantle becomes more rigid with depth. Ray 2 also passes through the mantle. It approaches the core mantle boundary at very low angle and continues its curved path. It reaches the crust at 103 degrees from the earthquake source. However, if ray 2 crossed the core mantle boundary, it would take a very different, see if we can see the figure at the same time, at a very different path. This is shown as ray 2A. Okay, so here's ray 2A. It would cross the boundary at a very low angle and get refracted strongly toward the core. This is because of the physical differences between the core and the mantle. Ray 3, right here, also crosses the core mantle boundary, but at a much steeper angle than 2A. It is refracted less strongly into the core. Compare what happens to rays 2A and 3 as they exit the core. So here's ray 2A exiting the core, and here's ray 3 exiting. They both travel back into the mantle and are refracted once more. However, ray 2A meets the boundary at a lower angle than ray 3. Ray 2A is refracted more strongly and reaches the surface farther than 180 degrees from the earthquake source. In contrast, ray 3 strikes the core mantle boundary at a higher angle. It is refracted less and reaches the surface at 143. All right, so here's where ray 3 reaches the surface at 143 degrees. Notice what happens to ray 4. It strikes both boundaries at steep angles. It is deflected much less than ray 2A and 3. Thus, the angle of refraction depends on the angle at which the rays strike the boundary or the core mantle boundary. The lower the angle that the rays strike the boundary, the higher they are refracted. So they were pointing to 4 right here. Okay. So in figure 7, the pathways of seismic waves passing through Earth's interior. Earth's core creates a shadow zone between 103 and 143 degrees away from the earthquake source. So here's that shadow zone between 103 and 143. All right. Whenever an earthquake occurs, there is always a large area on the opposite side of the Earth where seismic waves do not travel. This is called the shadow zone. The shadow zone for P waves is located between 103 and 143 degrees, which we showed before. The shadow zone occurs because the core blocks the seismic waves. The location of the shadow zone is a result of the physical properties of the mantle and the core. Seismic studies have enabled scientists to calculate that the core mantle boundary is about 29 kilometers below the surface. All right, so the core mantle boundary. Let me zoom out so we can see these figures as we're talking about it. A shadow zone also exists for S waves. The core has very strong effects on whether S waves can pass through it. P waves travel through any solid, liquid, or gas substance. S waves, however, only pass through solid material. They cannot pass through liquid. No S waves are received beyond 103 degrees from the source of an earthquake. This creates a massive shadow zone. This zone is almost one hemisphere in size. See figure 8. So figure 8 shows that the shadow zone is almost a hemisphere, which means it's almost half of the sphere. All right. S-wave shadow zone provides evidence that Earth's outer core is liquid because it blocks S waves. Recently, scientists have observed, let me zoom in because it's about to show figure 9. Recently, scientists have observed some very weak P waves within the 103 to 143 degree P wave shadow zone. This is shown in figure 9. Weak P waves emerge at around 120 degrees from the earthquake source. This suggests that Earth's core is divided up into liquid outer core and a solid inner core. The boundary of the solid inner core deflects the weak waves into the outer core. They continue through the mantle and to the surface within the shadow zone. So these are weak P waves in the shadow zone, revealing the presence of an inner and outer core. Okay. And there's, all right. The network of seismic monitoring stations around the world allows for the accurate recording, let me move down a little bit, of variations in seismic speeds. Using this information, scientists have been able to make inferences about the structure of the planet. For example, the moho represents the base of the crust and a change in the composition towards much denser silicate minerals. The moho occurs 5 to 70 kilometers below the surface, depending on the type of crust. At 100 to 250 kilometers below the surface, the Gutenberg low velocity zone occurs. Here the mantle is near to its melting point, although less than 5% is probably liquid. Nonetheless, liquid films that surround the mineral grains of mantle rocks slow the passage of P and S waves. This zone within the asthenosphere is very important for the plate motion. Without this weak and ductile zone, the upper and lower mantle would be locked together and the movement of Earth's lithospheric plates would be significantly reduced. So this is showing seismic velocities at depth in Earth. Okay, so you have your depth and your velocity. Seismic tomography. Seismic tomography. Earthquakes occur often around the world. As a result, scientists are able to analyze the speeds of hundreds of thousands of seismic waves as they travel through Earth in different directions. Using this data, they have produced images. These images reveal zones within the Earth where seismic waves move faster or slower than normal. Experiments have shown scientists that seismic waves are slowed unusually. Experiments have shown scientists that seismic waves are slowed by unusually hot rock. So here we go. Hot rocks are typically less rigid than cooler rocks. The study of three-dimensional imagery from seismic data is called seismic tomography. Look at figure 11. The tomography shows the upper mantle to be cooler beneath the continents and hotter beneath the ocean floor. The hot blobs in the mantle are located along mid-ocean ridges. Hot blobs also appear in zones of mantle upwelling. In both places, seismic waves have reduced speeds because the rocks are hotter and less dense than surrounding rock. Gravity anomalies. In physics, you have investigated Earth's gravity. You have learned that a body of falling to Earth will accelerate at 9.8 meters per second squared. However, to use one value only, you must assume that Earth is uniform. In fact, the topography on Earth's surface is highly irregular. Both the continents and the oceans contain mountains, flat regions, and valleys. Also, some of the surface is covered by ice. Other parts of the crust have caves that contain little matter. In addition, as you have read, oceanic crust is thinner than continental crust. Earth's interior varies both vertically from the base of the crust to the core. It is also very. Hold on, they did not type this correctly. It should say it also varies laterally. Some parts of the mantle are hotter and therefore less dense than others. Gravity is directly related to mass. Because different features contain more or less mass than others, very small variations in gravity exist across the surface of the planet. Anomaly is a word used to describe variations of what would normally be expected. NASA and the German Aerospace Center have launched the GRACE mission. This is the short form for Gravity, Recovery, and Climate Experiment. Its purpose is to measure anomalies in Earth's gravity. The measurements will be more precise than ever before. Scientists will use this data to make inferences about Earth's surface and interior. Let's go back to 140. Actually, let's zoom out a little bit so we can see more. Okay. Data is being collected by twin satellites in the same orbit. The satellites are separated by 220 kilometers. So this is the partnership between America and Germany. A partnership between NASA and the German Aerospace Center. Okay. The satellites are separated by 220 kilometers. They are traveling at an altitude of 460 kilometers above Earth's surface. The lead satellite speeds up when it detects very small increases in gravity. The second satellite uses a pulse of microwave energy to measure the change in distance to the lead satellite. The changes in distance are tiny. They are only about 1/10 of the width of a human hair. GRACE maps Earth's entire gravity field every 30 days. Changes in gravity over time reveal important changes in Earth's mass. Scientists can observe the distribution of ice sheets, bulges in oceans, and flows within Earth's water cycle. According to NASA, measurements since 2004 showed a decrease in gravity over the Antarctic ice sheet. This indicates a decrease in ice mass. This ice mass has decreased by about 150 billion tons per year. GRACE is also able to detect changes in Earth's crust. After the 2004 earthquake in the Indian Ocean, GRACE measured a decrease in gravity. This indicates that the density of the rock beneath the surrounding seafloor had changed. Before we talk about figure 13, I want to back up and talk about figure 12. This is a map of Earth's gravity anomalies showing regions of greater positive and negative variations from a calculated value of average gravity. Okay, so negative is blue and more positive is red. Now we're just looking at figure 13, so maybe I can zoom in a little bit. Figure 13. Figure 13 shows gravity anomalies. They are shown as departures from the predicted gravity of a smooth and uniform Earth. Some of the greatest anomalies, shown in red, occur in the middle of the Atlantic Ocean. They occur along the mid-Atlantic ridge. These are due to the occurrence of thick, dense oceanic crust. Whoops. Here we go. Figure 13. Gravity anomalies are shown by relief. Places where gravity is greater than predicted are shown in red, and by raised elevation, dark blue depressions indicate areas of lower than predicted gravity values. I suppose that would mean you feel a little bit heavier up here with the greater gravity, and then the dark blue where it's lower gravity than predicted. All right. Figure 14. Now hold on a second. Is that this? Yep, let me zoom out. So this is referring to, this section of text is referring to figure 14, so we're going to be able to view everything all at once. Figure 14 shows that at the very center of the ridge, the gravity value is actually lower than in the surrounding parts of the ridge. This is because at the center of the ridge, the lithosphere is very thin. The hot and less dense asthenosphere extends nearly to the surface. Rocks near the ridge have low seismic velocities of between 3.7 to 5.8 kilometers per, okay. The hot and less dense asthenosphere extends nearly to the surface. Rocks near the ridge have low seismic velocities between 3.7 to 5.8 kilometers per second. Figure 14 shows that velocities increase in all directions away from the ridge. So here's the ridge, and the velocity is increasing as you get away from it. The heat is higher at the ridge and decreases away from it. Alrighty. Oh, this is a measurement of gravity. Okay, so the gravity is increasing as you get away. This is a measurement of heat, which is the most near the ridge. All right, guys, where are we? Figure 14 shows that velocities increase in all directions away from the ridge. The rocks are more rigid further away from the ridge. In contrast, the Puerto Rico Trench has one of the most negative gravity anomalies on Earth. The trench is the deepest part of the Atlantic Ocean. It is over 8,400 meters deep. You can see it as dark blue areas. Here, the North American plate is strongly tilted. It is descending into the trench. Okay, figure 14. Let me move back up. Figure 14. Heat flow and gravity values reveal the internal structure of the mid-ocean ridge. Seismic values vary away from the ridge crest. They increase with depth and away from the center. The names of various igneous rocks that form oceanic crust are given. Basalt, gabbro, sediment. Okay, so those are some of the different names given. Like they said, the majority of the ocean floor is basalt. All right, guys. Okay.